a couple of those before we go charging on. I do have one administrative announcement, unfortunately, and that is that at 7 o'clock we have a tornado drill, and we're supposed to go down to the first floor and hang out in a reasonably safe area. Now, there's a center stairway here, but there may be more people trying to use that than the back stairway over here. So I suggest we go out this door, down this hall, go down that stairwell. And a very safe place would just be hang out in the base of our first floor in the stairwell. But someone has poked their head out occasionally, so we'll hear the all clear. I don't know if the speakers make it into the stairwell. Or we can wander out into the open area and have them say, "Get away, don't be anywhere that you can see a window. Flying glass." Okay, let's start with the laws of the limit. Yes?
Can we take our stuff with us?
You know, I would at least take my computers and calculators, you know, because I'd like to think everybody in the world's honest. But one time in this very building, I left a sweater, went back for it 5 minutes later, and it was gone.
Must have been a nice sweater.
I don't know. That was 30 years ago. I don't remember what it looked like now. Doesn't mean it won't happen again. Same guy may have gotten out of prison and come back to class. You know. Okay, let's talk about limits. If I have some function, f of x, and some other function, g of x, and I'm looking for the limit of f of x as x approaches some value a, and similarly for g of x as x approaches the same value of a. Well, let's say this does exist and is equal to L, and this does exist and is equal to, alphabetically, I guess, M. So, limits are very nice behavior, because the limit as x approaches a of the sum of the functions is simply the sum of the limits. The limit as x approaches a of the difference of functions is the difference of the limits. The limit as x approaches a of the product is the product of limits, and the limit as x approaches a of f of x divided by g of x is equal to L divided by M. And there's one caveat here. What would that caveat be?
M is 0.
M is not 0. Okay, so follows ordinary arithmetic. It does linear combinations. So if I have some P f of x plus Q g of x, the limit as x approaches a is PL plus QM. So this one really covers both of those and a host of others, because there's nothing to say that Q wasn't -1. And also works with powers and roots. The limit as x approaches a of f of x raised to the nth power is n times L, and the limit as x approaches a of f of x, the 1 over n is the nth root of L. This last one, there has to be a caveat, because if n is an even integer, I'm looking for an even root, so L cannot be negative. So in the case that n is even, L must be non-negative, so it can be 0 or positive. Then then it works. So arithmetic with limits is reasonably nice. We like those things. So let's look at another limit that we will be using along the way. I want to find out what is the limit as theta approaches 0 of the sine of theta over theta, where this must be in radians. This still exists if it's in degrees, but it has an additional pi factor that we have to take care of, pi over 180 factor that we have to take care of. But if I draw a quarter circle and say the radius of this quarter circle is 1, and that's from the unit circle. If I schematically draw some small positive angle theta, which is going to approach 0, then there are 3 segments I can show. Segment from that point straight down, perpendicular. That is the sine of theta. Because the sine of theta is the opposite over the hypotenuse, and if the radius is 1, the hypotenuse is 1, so it's just that segment. And if I extend this and do that, then this segment is the tangent of theta. Because now from here to here is 1, and tangent is the opposite over the adjacent. If the adjacent is 1, then the opposite is the tangent of theta. And remember, in radian measure, what's the definition of the measure of an angle? The measure of an angle theta is the arc length of length theta divided by the radius, in this case 1. The arc length divided by the radius is equal to the angle measure in radians. So this little bit of arc in here is theta. Now, it does not take a great discerning eye to see that the sine of theta is less than the arc theta, which is less than the tangent of theta. For all values of theta, which are small positive values. Okay. At 0, the sine of 0 is 0, the arc length is 0, and the tangent is 0. So at 0, they're all equal. But when they're not 0, that's true. And I want to find this limit. So what I'm going to do with this inequality is I'm going to divide everything by the sine of theta. Sine theta, sine theta, sine theta. And simplify. What's sine theta divided by sine theta for all theta? A number divided by itself is 1. 1 is less than theta divided by the sine of theta. And what is tangent divided by sine? Well, let's see. Tangent is really sine over cosine. Sine over cosine divided by sine. The sines divide out, and I have 1 over cosine. So this inequality is true. Okay. Well, since these are all positive numbers for theta greater than 0, then when I take their reciprocals, for instance, 3 is less than 4, we take their reciprocals, and 1/4 is less than 1/3. The order of the inequality will change. So if I take the reciprocals of these, reciprocal of 1 is 1, which will be greater than the reciprocal of sine theta over theta, which will be greater than the cosine of theta. So I have this inequality. One of the other interesting properties we have, if I have some function of f and some other function g, and this is some point a, of course, if f of x is greater than or equal to g of x for all values of x, yet the limit of f of x at a is equal to L, and the limit of g as x approaches a is L. That is, the limit as x approaches a of f of x equals the limit as x approaches a of g of x is equal to L. If I have any other function between these two, doesn't matter what it does, as long as it's between these two, fg, let's call this h. So if f of x is greater than or equal to h of x is greater than or equal to g of x, then the limit as x approaches a of all of these will be L is greater than or equal to this limit of h greater than or equal to L. So what must the limit of h be? Got to be the same thing. It's also L. This in different books I've seen under different theorem titles. One of them calls it the squeeze theorem, or another one calls it the sandwich theorem. Doesn't much matter. Clearly, if this is always less than f but greater than g, and f and g collide at a point here, that one's got to go through that point. Only choice. So we're going to do the same thing here. I want to take the limit of this as theta goes to 0. Limit as theta approaches to 0. Well, the limit of a constant is constant. Doesn't matter what theta is. Theta can be anywhere from negative infinity to infinity. The constant 1 is the constant 1. And limit of cosine as theta approaches 0. What's the cosine of 0? If you've forgotten, punch that on your calculator.
1.
It's 1. So if these two limits are both 1, what is that limit? What's the only number you can think of that's between 1 and 1? So when we get to the trig functions in the not too distant future, that's a very important limit. And if it's important for the sine, it may also be important for the cosine. But I want to look at one slightly different. I want to look at the limit as, once again, theta approaches 0 of 1 minus the cosine of theta over theta. At 0, the numerator we get 1 minus 1, which is 0. In the denominator we get 0. We have the indeterminate form 0 over 0, which in some cases later on we'll be able to figure out what that is. But here we don't know. So I'm going to go back to my rules here, and I think I'll use this rule, use this product rule. I'm going to pick a limit that I know, multiply this by, and that would be the number 1. Is 1 plus cosine theta over 1 plus cosine theta equal to 1 for all values of theta? Yeah. Although it also has Oh, no, it doesn't. It's perfectly happy because it varies between 0 and positive 2 for different values of theta. But if we look at the limit, let's go and do this multiplication. Limit as theta approaches 0 of 1 minus the cosine squared of theta over theta times 1 plus cosine theta. Well, what is another name for 1 minus cosine squared theta? Sine squared. So this is the limit as theta approaches 0 of sine squared of theta over theta times 1 plus cosine theta, closed. Okay. And I can choose to write this as limit as theta approaches 0 of the sine of theta over theta times the sine of theta over 1 plus cosine theta. What's the limit of sine theta over theta? What's the limit of sine theta over theta? 1. So, limit as theta approaches 0 of 1 times sine of theta over 1 plus cosine of theta. Now by direct substitution, the numerator is 0, the denominator is 2, 0 over 2 is 0. So we have these two nice pieces of information. Once again, must be measured in radians. The limit as theta approaches 0 of 1 minus cosine theta over theta equals 0. Okay. The sign-in sheet's going around someplace, and a couple of people have come in since. Throw this to your left, please. That's close to a throw. It was a slide. Okay. So, we have an intuitive idea of what a limit is. If I simply kind of draw a line here or a squiggle, leave a gap in it, go on, maybe put a point in down here beneath it. Doesn't matter where the axis is, I drew it the first quadrant just because it's easy. But at A, call this B, call this C, this is some function F. So F at A is well defined. F at A is equal to the value B. But the limit as x approaches A of f of x is not B, it's C. Because where does it look like you're going? As you're traveling down this curvy road, it looks like you're going to that point. If you're coming back the other way, as you're driving down this curvy road, it looks like you're going to that point. Boom. So if A equals C, later on we'll define continuity, and a continuous function, we can't have holes like this. And a function that's not continuous, we can have as many holes as you want to throw in there. Okay. Let's look at another. floor function is the greatest integer not greater than. In some older textbooks, for the floor function, floor of x, you'll see as int print x, means the integer part of the function. Okay. More recently, they've changed the notation. I like the new notation. Oh, an older notation also was like this. It's a boldface square bracket. So if you're looking in some old books, you may either see this or this. Both of these mean floor. So we're on the second floor. No matter where this marker is held, somewhere between way low and way high, its floor value is 2. So having said that, what is its ceiling value? The next integer up. So the ceiling of the second floor is basically the floor of the third floor. So ceiling is what it says. What floor would we be on? What integer would we associate with the ceiling? And the integer we'd associate with the ceiling here is 3, here with 2. And the symbols for these, spelling this one out, this is the least integer not less than. And the O symbol for it was similar to this, except it was backwards. But someone not too many years ago said, hey, let's quit calling them the greatest integer not greater than and the least integer not less than, and having these symbols that by appearance don't remind you of what it is. Let's go to intuitively, what is that function? Ceiling. Intuitively, what is this function? Floor. So those are the symbols we use now. So having said that, your age is a good floor function, whereas postage is good ceiling function. If your letter that you're sending weighs next to nothing, it still requires a whole 1 ounce cost stamp, 55 cents now. If it's a gnat's eyelash, if gnats have eyelashes, they don't. But gnat's eyelash heavier than 1 ounce, then you have to pay for the full 2 ounces. So this is the taxi cab or stamp function, where you buy something $3 for $1 and you buy one of them. What do they charge? They don't charge you 33 1/3. They charge you the ceiling, 34. So these come in handy occasionally. Okay, but if we look at age, now I know when someone's born, they tend to say, oh, he's just brand new, 3 hours old, but looks just like his daddy. Now be truthful with me. Have you ever looked at a very young baby who has really gone through an abusive experience and may very much look like a prune or something shortly after birth? They don't look real good. Oh, they're so good. Then you count days, and you count weeks, and you count months, and you know, and you may do that up to about 2 years old. But we're gonna do the classical birthday. When they're born, they're 0, and they stay 0 until they are suddenly 1. And they stay 1 until they're suddenly 2. And they stay 2 until they're suddenly 3. And so on. We have age versus ceiling age. I'm 73. I will remain 73 until I'm 74. Okay.
uses the floor symbols of, but you said ceiling age.
Oh, well, it is floor. Because I'm more than 73, but I'm not 74, so I use this value, not that value. Okay. Age is a floor function. Age is a floor function. Taxi cabs are a ceiling function. Okay. So, what is the limit as age approaches 2 of age? Not a problem. Because if we approach 2 from here, we're 1, we're 1, we're 1, we're 1, we're 1, we're 1. So where does it look like we're going? It looks like we're going to the value 1. On the other hand, if we're with Doctor Who and regression and regressing with time, we're 2, we're 2, we're 2, we're 2, we're 2, and it looks like we're going to 2. So when we have a discontinuity in a function, not just a point discontinuity like I sketched over there, but a jump discontinuity, then we have to think of a new concept for limits. And the answer is we look at what we call left-hand limits and right-hand limits. That is, we look at limits coming from the negative side of the point. It may not be a negative number, but from the negative side. Or we look at a value coming from the positive side. So this does not exist. Even though coming from the left, I'm just going to shorten that to A. The limit as x approaches 2 of floor x. If I approach it from the negative side, I get 1. Limit as x approaches 2 from the positive side of the floor function, I get 2. Because that's where it looks like you're going. So we'll be looking at quite a few of those here in a few minutes when we get to working exercises. But now we'll talk about limits informally. Let's see if we can define a limit formally. So this will be in section 2.3. And again, kind of setting it up. I have some function, and just for convenience, for the first quadrant, but it may be anywhere. And at some value A, I expect the limit is L. Okay. And this is my function f. So we say limit of f of x as x approaches A is equal to L if given epsilon greater than 0. One of the Greek letters, alpha, beta, gamma, delta, epsilon. Then there is delta greater than 0 such that the absolute value of x, no, I'm sorry. x minus a is less than delta. And when absolute value of x minus a is less than delta, comma, f of x minus L, absolute value, is less than epsilon. Well, let's pick an epsilon on this drawing. I'll pick it there. This distance is epsilon. This distance is epsilon. Same distance above and below my intended target. If I run parallel lines out to the function, okay, and then drop perpendicular lines to the axis. Now, if it's on down here, the parallel lines would still go out, but the vertical lines would have to come up. But in any event, because this is curving, perhaps, one side may not be this as large as the other side. So it is sufficient to pick delta 1, delta 2. Delta is the minimum of delta 1 and delta 2. When it's concave up, as this is, it'll be the delta 2. If we're concave down, the choice would be delta 1. Because this right-hand side here is a little narrower than the left-hand side. But you see, anytime I pick a value of x inside delta from A, it puts me in this area there. Which means projecting those values up to the function, it means the result is inside of L, or in the epsilon interval around L. Now, algebraically, that is difficult to work with. Okay? If it's linear, very nice. If we have a linear situation around our point, and this has some slope m, and we're given epsilon, then we pick delta to be less than epsilon over the slope. And that works. But if it's not linear, we have to work a little harder. So if we have something that's not linear, I want to pick a slope on this side, and if it continues to be concave upward, I'll arbitrarily pick 2 points to the right and find the slope of the secant line and then pick delta to be less than epsilon divided by this slope. So, the art of finding an appropriate delta is a bit of a pain. So, if you look at your syllabus now, and look in the back where, I guess it's page 3 of your syllabus, second sheet, where it says Module 1, and you read down and see what problems it asks us to do out of section 2.3. What problems are you being asked to do out of section 2.3? None? What was the course coordinator thinking? Oh, the same thing I'm thinking. This is a pain in the backside. when I had Calc 1 back in the manual days when we had no calculators and had to do this by hand, this killed most of us. You know, the next quiz, our 98s went to 72s, but we recovered with after we quit doing it this way. So in order not to cause too much pain, surprise, surprise, there are not any problems suggested from the text for section 2.3. There will not be any like this on the quiz, and there won't be any on the first test. I know that just breaks your heart, doesn't it? Having said that, let's now jump into section 2.4. And in section 2.4, what we're doing is looking at limits from the left and limits from the right. Okay. And intuitively, we do it the way we did when we're looking for limits in general. So, for the next extended amount of time, I think I'm going to turn to section 2.4 and glance down, and see if there are any surprises. Oh, there's one that I do want you to look at in 2.2 that we didn't look at. Let's look at the sign of 1 over x, limit as x approaches 0. If you put that on your graphing machine, the curve is asymptotic, that side is asymptotic over here. It never climbs above 1 or below -1, so it's bounded. But as you come in, there are infinitely many periods of the sine function between any small positive number and small negative number. So, if you try and pin this down at 0, it doesn't pin down, because you cannot satisfy this definition. No matter how small, if epsilon is anything less than 1, then there's no delta that exists that will force this answer to be within 1 of that, or within epsilon of that, because it always, infinitely many times, bottoms out at -1 and tops out at +1. They do a halfway decent drawing of that. Let's see where they did that halfway decent drawing. There's one, half the drawing on page 65. Thought they had another one of it. That looked pretty good. Maybe back in 2.1. So page 65, right hand, middle of the right hand side, it shows a reasonable sketch of that. On the other hand, looking at one very similar to it, the limit as x approaches 0 of the square root of x times the sine of x, or sine of 1 over x. Now remember now I erase that word right here, the rules for operating with limits. We can add limits, we can multiply limits, we can divide limits, but here we have a problem. As x approaches 0 in this indicated product, this one behaves very nicely. What does the value of the square root of x go to as x approaches 0 from the positive side? Because from the negative side it's undefined. But from the positive side, where's this going? 0. Now this side, if it were infinity, 0 times infinity is an iffy. Yes, there are cases where we can define that product to be some finite number, but we don't have to go there. What is the most that sine of 1 over x can be?
1.
What's the least sine of 1 over x can be? So the product must lie between 0 times -1 and 0 times +1. And what's the only number that lies between 0 times -1 and 0 times +1? 0. So this limit does exist, and it's 0. That is, if I come at it from the positive side. Okay, so let's look in section 2.4. That's where they're talking about these one-sided limits. And let's work a few of them. So, beginning with, on page, what is it, 79? Yeah. No, that's 2.3. 2.4. On page. Yeah, there's a good picture of that sine curve on page 86 that I was talking about. Page 88. Now, often many of the problems that you're assigned are odd numbered problems, and they have answers in the back of the book. I choose to do the even numbered problems in class for 2 reasons. One, because the answers aren't in the back of the book, so if you want an answer, you have to depend on me. And 2, if I make a mistake, I erase it at the end of the hour, so the people coming in afterwards don't know that I was temporarily an idiot. Having said that, once again, when you see me make a mistake, please speak up then, so that you and your peers do not leave the room with the wrong information. So, I think I'll start with number 2 and do every other even. So that'd be 2, 6, 10, 14, and so on. Okay. So number 2, they give us a nice function and ask us several questions about it. Let's put a drawing up, see if I can get it replicated. So we have this drawing, and from -1, 1, it kind of semicircled downward to the origin. And at the origin, we have the point 0. And then from 0 to +1, it seems to climb something like a parabola, perhaps not. Okay. And at 1, it assumes the value 1, 1, 1, skips 2, it goes to 3. So there's my sketch. Now, observing this sketch, x, f of x, or y. Let's find these things. What is the limit? As, number A, as x approaches -1 from the positive side. Okay. Limit f of x as x approaches -1 from the positive side. Well, here's -1. Here's the positive side of -1. So as we approach -1 from this side, where does it appear to be going and where does it go? Goes to 1. B. Limit as x approaches 2. Limit as x approaches 2 of f of x. Now the book says does not exist, but they want us to answer it true or false. So why don't we find the answer? Does this have a limit as x approaches 2? Coming from this way, it looks like it's going to the value 1. Coming from that side, it's going to the value 1. So this limit does exist. That limit is 1. So the statement in the book is false. Number C. The limit as x approaches 2 of f of x is 2. Well, C, limit as x approaches 2 of f of x they claim is equal to 2, and this is clearly false because we know it's already 1. So what they actually asked was does not exist. D and E, that means does not exist. Okay. And this was false. And this was true. Okay. Number D. Limit as x approaches 1 from the negative side. D. Limit as x approaches 1 from the negative side of f of x. Approaching it from the negative side, where does it look like it's going? As it approaches 1 from the negative side, where does it look like it's going? 2. And what do they say? 2. So that is true. DE. Limit as x approaches 1 from the positive side. E. Limit as x approaches 1 from the positive side of f of x is, approaching 1 from the positive side is 1. And I think that's what they said, so this must be true. So number F is also a true statement because it combines these. And if the limit from the left is not the same as the limit from the right, then the limit does not exist. The limit as x approaches 1 of f of x does not exist. G. Limit as it approaches 0 from the positive side is the same as the limit as it approaches 0 from the negative side. From the positive side, it looks like it's going to 0. From the negative side, it looks like it's going to 0. They are equal. That's a true statement. H. The limit of f of x exists at every point C in the open interval from -1 to 1. In the open interval, from -1 to 1. That does not include the endpoint. If it was a closed interval, this statement would be false because the limit does not exist at 1, but exists for anything just short of 1 or just greater than -1. The limit exists. So that's a true statement. Number I. The limit f(x) exists at every value C in the open interval from 1 to 3. And from every open interval from 1 to 3, yeah, it is 1 everywhere. The limit is 1 everywhere. Okay, so that's true. J. The limit as x approaches -1 from the negative side. And they said it's something?
0.
Let's look at my function again. Nope, they don't have anything drawn. So what's the domain of this? The domain of this function is from -1 to 1. We can't come at the function from the negatives from below it, so it's not defined. And we can't come at from above down to 3. It's not defined. Because there are no values of the function defined on this side to talk about saying where does it go. We know where it is at -1. We know where it is at +3. But beyond our boundaries, there's some theories about multiverse. Okay? Do any of us have any idea whether that's true or not? Can we see a multiverse? Do we know which direction to go to get to the next one? Or what black hole we have to fall into, or what wormhole we have to take our craft through? Okay. And K. Same thing, isn't it? That's from 3 from the positive side. Yeah, it doesn't exist. Okay, number 6. Okay, and I put this one up on the board already. It was over there. I didn't draw the picture, but that's number 6. Let g of x equal square root of x times the sine of 1 over x. They did a pretty fair job of sketching it. You have a series of compressing sine waves that are collapsing to 0 because of the multiplier in front of it. Number 10, we have a piecewise defined function, and it is defined for all real numbers. So let's sketch that one clear over here on this board. Number 10. F of x is equal to one of 3 things. It is either equal to x, or it's equal to 1, or it's equal to 0. It is equal to x when x is between -1 and 0, or between 0 and 1. -1 is less than or equal to x, is less than 0, or 0 is less than x, is less than or equal to 1. One is less than x, is less than or equal to 2. Oh no, I had that wrong. 1 is less than or equal to x. Oh, and I have this wrong. Get all the signs right here in a minute. Okay. No, wait a minute. Man, helps if you look at the right problem. I was right the first time over here. But what did this one say? Yeah, that one. And then the last one says 0 when x is less than -1.
Are we doing 10?
Yeah, x is less than -1, or x is greater than 1.
10 has x equals 0 on number 1.
1 is supposed to be x equals 0. You might have been looking at number 9.
Oh, yeah. Yeah, I'm sure I was. Now the eraser has escaped me. Okay. All right. So let's draw this. My key places I have to look are -1, 0, and 1. And between -1 and 0, we have this. Because it says fx equals x. That's a straight line, slope of 1, y-intercept of 0. Or we have this. Also a straight line up to there. So we have a straight line, endpoints included, but the middle point is not. skipping down to the third line, we have that, and we have this. Now picking up the middle line, we have when x is 1, checking signs again. 10, 10, 10, 10, 10. Less or equal. Next one. Oh, yeah, okay. When x is 1, we have 0. Okay. So there's my pretty picture. 1, 2, 1, -1, -1, -2, and so on. Okay. So let's answer the questions they pose. 4 questions. What are the domain and range of f? The domain, negative infinity to infinity. Every point is defined. The range is from -1 to 1 inclusive, because it includes -1 and includes +1. Okay. Number B, at what point C, if any, does the limit as x approaches C exist? The limit as x approaches C exists anywhere to the left of -1, anywhere to the right of +1, and anywhere on the open interval from -1 to +1. The only place that the limit does not exist is there and there. Because here, from the left, the limit is 0. From the right, the limit is -1. Over here, from the left, the limit is 1. From the right is 0. But everywhere else, the limit is what it looks like it ought to be. Okay, and D. At what point does the left-hand limit exist but not the right-hand limit? And at what point does the right-hand limit exist but not the left-hand point? Well, for this, at every point a left-hand limit exists and a right-hand limit exists. But there are 2 points where those values are not the same. Number 14. Limit as x approaches 1 from the negative side. Limit as x approaches 1 from the negative side. I have 3 rational expressions. Rational expressions being 1 over x plus 1. Next one is x plus 6 over x. And the last one is 3 minus x over 7. Okay. Now, as x approaches 1 from the negative side, do we have any issues? If this were a minus sign, x minus 1, then x approaching this from the negative side would be different than x approaching this from the positive side, as far as this sense goes. As approaching from the negative side, we're dividing by a negative number. approaching at this from the positive side, we'd be divided by a positive number. But since we're talking about positive 1, close to positive 1, this value is close to 2. Close to positive 1, this value is close to 1. At positive 1, this value is close to 7. At positive 1, this value is close to 2. So we can do this by direct substitution because we have no issues. So 1 over 2 times 7 over 1 times 2 over 7. Number 18. Limit as x approaches 1 from the positive side, and part B as x approaches 1 from the negative side of that same issue. Let's see, root 2x times x minus 1. Okay. So we have this function. Root 2x times x minus 1 over the absolute value of x minus 1. Limit as x approaches 1 from the negative side, and the limit as x approaches 1 from the positive side. Root 2x, x minus 1 over absolute x minus 1. Okay. They look identical, but look at the sign of the quotient. This, as x approaches 1 from either way, this approaches square root 2. As x approaches 1 here, or here, or here, or here, those are approaching 0. But what is the sense of direction for these? As x approaches 1 from the negative side, this thing is negative. For instance, if x is 0.9, this is negative 0.1. But if we're approaching that same value from the positive side, if this is 1.1, that's positive 0.1. Down here, inside the absolute value, this is negative, but absolute value does what to it? Makes it positive. And here, inside the absolute value is positive. Absolute value keeps it positive. So up here, this goes to negative 1. Down here, this goes to positive 1. Result is minus square root 2 there and plus square root 2 here. Absolute value will do that to you sometimes. If in doubt, build a table of values. Build a couple of table of values. 0.9, 0.99, 0.999, 1.1, 1.01, 1.001, 1.0001, 1.00001. And crunch those out on your calculator. And you'll see the closer you get to 1 from the negative side, your calculator will say negative 1.414. Closer you get to 1 from the positive side, your calculator will say positive 1.414. Test out on a calculator if you have issues with that. Okay, let's take a moment. If you look at your schedule on your syllabus, it says that we have an activity coming up which says on quiz day I'm going to distribute this early. Not that early, but early. So, and I'll even help you through a couple of them. Of course, the two I'm going to help you with are the easiest two. So you get the idea of what we're doing. Or this is ready for my phone. And you get the long stretch where you can be the gentleman and come get it. She tried. So, I have a square array of points. I want to make squares by connecting 4 points from that square array. So the question is, how many different squares can I make by connecting dots here? Not a tough question, folks. 1. Well, if I increase my rectangular array from 2 by 2 to 3 by 3, now, how many squares can I form? I heard of 5. Anybody else have another number? 4 is another number. Well, let's count. 4 little squares. 1, 2, 3, 4 little squares. 1 big square. We're up to 5. I heard someone just now say 6. Where do you see 6?
You connect the top middle to the
Oh-ho! Aha! So there's your hints. We have to think inside the box, but we can lean a little. Okay. And you can only count the squares whose vertices are on 4 of the given points. Because when you start overlapping squares with squares, then maybe you get some smaller squares, but they don't count. Just the big squares. Well, the 1 by 1s and larger count. So, there's 1 and 2 done. All you have to do is come up with the other 8. Or 9, the other 9. And maybe a formula for it, or maybe not. But of course, since this is an activity, activities are open book, not this book, open note, open friend, open classmate, open math lab tutor, open Google, open
What about
Foxfire.
What about open teacher? Can we ask you? This is part of the
At least for now. Okay. Yeah, teachers, once they distribute an exam, suddenly become stupid. They know no answers after that. You know, until you turn it in, then suddenly the answers come back to me. Oh, so. Okay, going on. That was number 18. Number 22 says use the graph of the greatest integer function. Greatest integer not greater than the floor function. Use the graph of the floor function
figure in 1.10, section 1.1, to help you find the limits in exercise 21 and 22.
We're doing 22.
Yeah, I'm doing 22. So what does 22 tell us? Besides we're dealing with the floor function. And remembering the floor function starts there, goes, jumps, goes, open, jumps, goes. And the same to the left of 0. There's a sketch.
And number 22 says, the limit of t subtract the floor of t as t approaches 4 from where? From the positive side.
I need at least 2 more of these. So 3 goes here to there. That goes from there. 4, 5. The limit of the floor of paren t minus floor t closed as t approaches 4 from the positive side.
And T is your X parameter.
Yeah. Just so at 4, this is 4, and the floor is 4. We get 0.
But from the negative side, because it does ask that, doesn't it? Yeah.
From the negative side, t goes to 4. Floor of t stays at 3. So it becomes 1. This is 0, but the limit as t approaches 4 from the negative side of t minus the floor of t is 4. So this is coming to 4, and this is staying at 3. As we move along here, the value of t is increasing toward 4, but the value of the floor function is not increasing. It's staying a constant 3. It doesn't matter that the value of t minus floor of t at 4 is 0. What matters is, where does it look like it's going? And where it looks like it's going is 1. 4 minus 3, 1. Coming back the other way, it's 4 minus 4 is 0.
Okay, number 26. Limit as h approaches 0 of h over sine of 3 times h.
Limit as h approaches 0 of h over sine of 3 times h.
Well, let's do a little thinking here. I could expand the sine of 3h by breaking into sine of h plus 2h. and writing as using my trigonometric identities. And that's one way to do it. And we'll do it that way this first time. So this same as limit as h approaches 0 of h over, sine of h plus 2h will be sine h cosine 2h plus cosine h sine 2h. Agreed? So doing it that way, we get sine of h times cosine of 2h plus cosine of h sine of 2h. Okay. Let's see how this denominator behaves as h approaches 0. Cosine of h is 1. What's sine of twice 0? Sine of twice 0 is 0. 0 times 1 is 0. Okay. So this can go away. And cosine of 2h is 0. No, I'm sorry. Cosine of 2h is 1. 1. 1 times sine h. Oh. So it kind of looks like sine h over h. But it isn't, because these actually have an impact. So this doesn't really lead us to the solution we need. But we can do a simple substitution. Let's write this as the limit. Let's say 1/3 the limit as h approaches 0 of 3h or the sine of 3h. And further, let's make the substitution 1/3 the limit as a approaches 0 of the sine of, a over the sine of a, if I let a equal 3h. Let's look at this one. What is the limit of a over sine a? What we proved was that the limit of sine a over a is 1. So the limit of a over sine a is the reciprocal of 1. That's 1. Which means that's 1. But each of these have a leading coefficient. In general, limit as h approaches 0 of the sine of n times h over h. An interesting result. Okay. That was 20, what was that? 22, next up. Oh no, 22 was the T problem. That was 26. Okay, 26 is 1/3. Number 30. Limit as x approaches 0 of 6x squared cosine x cosecant 2x. Woo!
we write this one down correctly. Limit as x approaches 0 of what does it say? Someone read it to me. Number 30.
6x squared. In parentheses, cotangent x. Parentheses, cosecant 2x.
Over. Oh, that's just it?
I think that's
Oh, okay. Well, let's rewrite this. Cosecant, not cosine. Cosecant. Limit as x approaches 0 of 6x times cotangent x times x over sine 2x. Let's rewrite this. Three times 2 is 6. X times x is x squared. There's my cotangent x, and here's cosecant 2x. Goes from the numerator as cosecant to the denominator as sine. We just worked this problem. That is 1. What do these do? What is the cotangent at 0? What's cotangent of 0? No, it's not. Tangent is 0, so what's cotangent of 0? Undefined. Really big. Then we have an issue. Oh, well, let me rewrite this. This is 1. I'll just worry about this now. 3x times cosine x over sine x. As x goes to 0, what does cosine do? No, cosine of 0 is 1. So let's write this way. Limit as x approaches 0 of x over sine x times 3 times cosine x times 2x over sine 2x. X over sine x goes to where? 1. 2x over sine 2x goes to 1. 3 times cosine x, cosine goes to 1. What's 3 times cosine? 3. 1, 3, 1. Now, like I say, supposedly,